Let me check.
Yeah, double check.
Wait a minute.
Sure.
Carol, I corresponded with Carol.
Carol?
Carol, I think. Carol and Adam. Okay, maybe it works.
Sure.
Good morning. Today is our lecture number 21, and I will consider an example to what we did past time. I will consider some numerical example where there is this element that is a three-dimensional element. The other parts are free. That means that in reality, this element looks like this. Here there is stress, which is minus 20 megapascal. Then there is a shear force here, but this face and other face are free. So here, because there is a shear force, then that means that there should be shear forces also in this direction. Now, if I take some of the moments with respect to this point, then this shear force and this shear force should equal to each other, and they equal to 60 megapascal. Then if there is a shear force here, there should be shear force in opposite direction, like so that some of the forces in x direction would be 0, some of the forces in y direction should be 0, therefore this shear force equals to this one. So there are 4 equal forces acting on 4 faces, but here there is, of course, another sigma, which is minus 20. So sigma x equals minus 20, sigma y equals 90 megapascals, that is 90, and tau xy equals 60. So then we calculate, that is this one. Oh, I somehow did not show the element. I will zoom. Okay, so that is this element. Now we are finding the, so there is, it turns out, somewhere where if we had cut this element in different directions, we would get different stresses. Now it turns out that there are some directions, so-called principal directions, where shear forces not act, where only the normal moments are acting. And they are attaining maximum or minimum value or extremal value. So that is tangents 2 theta principle equals tau xy divided by sigma x minus sigma y divided by 2. So then it is 60 divided minus 20 minus 90 divided by 2. So from here we find tau 2 theta principle equals minus 47 degrees and then 49. Or theta p equals minus 23.7. Difference between theta p1, so there are 2 directions naturally, because we need to have a cube also in new coordinate system. 2 theta p1 and 2 theta p2 is 180 degrees. So 2 theta p1 then equals 180 plus 2 theta p2, and equals then 180 minus 23 equals 132 minus 47 equals 132.51. From here we get theta p1 equals 66.3 degrees. theta is measured positive counterclockwise, as it was explained to you in Strength of Materials course. So I will show you entire page here, so that those who want to write could write. You are getting these pages, I will scan and put on the canvas. However, still it is good to write down while you are sitting, otherwise suddenly you feel you have nothing to do, then you are distracted, you are maybe doing something else. I very much hope that you are not listening to music at the same time as you are listening to me. And look, please, I'm not saying it randomly. There are these recommendations by Oprah Winfrey. And recommendations were given before coronavirus, but they seem now very, very apropos. It says that be present, okay, that's with whoever you are with at any given moment. Okay, so now you are with me. But particularly the people you care about. Presence is the most valuable gift you can give. So please give this gift to yourselves and to me. Please listen. You are listening to the lecture, so please listen. Everyone you know is looking for your presence. When someone is upset, when you want to know is, are you present and hearing me? Okay? And that was done before coronavirus. So the formulas for sigma maximum and minimum are principal stresses. So these are principal stresses. Sigma 1 to equals, and that is a formula. That is sigma x plus sigma y over 2 plus minus sigma x minus sigma y over 2 squared plus tau x y squared. So that is minus 20 sigma x plus 90, sigma y equals 90, divided by 2, plus minus. Minus 20 minus 90 over 2 squared, plus 60 squared. So that is 90 minus 20 is 70, 70 over 2 is 35. Plus minus, and this value equals 81.4, I calculated. So sigma first equals sum, 116. And second, so I'm using Roman notation. I am using Roman notation because we are getting two roots. Sigma 1, and that is sigma 2. So now, what is the maximum? Now we would like to write what are sigma 1, sigma 2, sigma 3, because that is, you always, any condition, even if it is two-dimensional, and this was a two-dimensional state, but it is three-dimensional element. So, look please. Sigma 1 is a maximum of sigma 1, sigma 2, sigma 3. Sigma 3 is a minimum of sigma 1, sigma 2, sigma 3. Whatever is left is sigma 2. So now, look please. This phase does not have any stress, so that means that stress in this direction is 0. So this is one of the principal phases. So what we are doing is we are not, so that means that we are, this phase is one of the principles, we are looking at other principal directions. So here, sigma first, so that is 116, so that is maximum of 116, then minus 46.4 and 0. So that is 116. Minimum of these 4 equals minus 46, 4. And sigma 2 is 0. So that means that now how much is tau maximum? Tau maximum is tau maximum equals sigma 1 minus sigma 3 divided by 2. Okay? So that is sigma 1, that is sigma 3 divided by 2, is then 160.4 over 2, or 80.2 megapascals. So we found that around this point, we could make different cuts. There will be no cut where the stress will be bigger than 116. There will be no cut where stress will be less than minus 46.4. And there will be no cut where shear stress will be bigger than 80.2. So we found everything. We did like a surgical operation. Of element in stress state. Any questions? Okay, now we want to apply this theory to something. Skew bending. Bending in two planes. So we studied something that is called, so what happens when bending occurs not only, let us say like this, in Z, in plane perpendicular to Z. That means in plane OXY. Or maybe there are loads here. Okay, beam does not know that we studied in strength of materials only in this case. Beam may act with forces in other directions. So QY, so imagine that, sorry, there is a load, distributed load QY. QY results in shear force VY and bending moment MZ. That is called direct bending. Direct bending is bending in one plane. Now, more general case is like this. This one, that is called skew bending. Look, there is this beam, analogous beam of the same beam, and there is a force in y direction, but there is also a force that is a concentrated force, P sub z, in z direction. So that means that this beam bends in OXY plane and also OXZ plane. Sorry. Any questions? So that is what we are going to study. Now, sorry. We learned this formula in strength of materials. Sigma equals m divided by I times c. Or, that is moment of inertia, that is the biggest distance. So if moment acts here, then that is here. External fiber. That is where the stress is biggest. So this I over C in American literature is often called section modulus. In German literature, it is denoted by W, and then sigma equals M divided by W, which is a mirror formula. Mirror formula is good to remember because it helps you to remember this form. So mirror way is the simplest possible way of writing this formula, so to say. That is this one. Okay, now we have this beam. That is a beam, that is the axis. I can depict it differently also, but I depict it here like this. So due to distributed load, bending moment looks like this. That is a bending moment diagram. Mz. And this equals QYL square over 2. Okay? Now, look, please. This is a bending moment with respect to the axis. We depict it in the plane OXY. So that is this OXY plane. Now, this load gives a bending moment with respect to y-axis. So we should depict it in X or Z plane. And X or Z plane, that is this one, P times L. That is this one. My, P, Z times L. So two diagrams in one picture. Okay? Now, we have to use analogous formula for each place. So this is the biggest value, naturally, of the bending moment. Look, please. So, as I said, C is a distance from neutral axis to, that is a neutral axis. Two extreme fibers. Moment equals Iz, for example, equals, so imagine 2 times 6 cubed divided by 12. Now let us consider this rectangular cross-section. So distributed load acts on top, down. That means that upper fibers are in tension. So here there is stress plus, and here is plus. So I will write here plus. So that is how they vary. That is a cross-section. Stress is positive, and then straight line at neutral axis 0 and negative. So here and here are negative because of Mz. Okay. Now, because of My. Okay. These fibers, okay, whatever are here, will be in tension, and the other, sorry, compression, because P so presses up. Okay, presses up. So that is compression, and the other will be in tension. So that is compression. Yeah, I have another figure. I do not put it together. So now stresses are like this. That is a cross-sectional area, that is compression, then that is a neutral axis, goes to different values. That is a straight line. So that is minus and minus, here is plus and plus. So that is My. So here stresses are equal. Bending moment, that is a bending moment, divided by Iz and C. Cy equals just 3. 6 over 2 equals 3. Here Iy equals 6 times 2 cubed over 12. Cz equals 2 over 2. So that is, so pay attention. So here I have from bending moment mz plus, bending moment my plus. Here will be bending moment mz minus, bending moment my minus. So these 2 points are dangerous points. Here will be maximum tensional stress. Here will be maximum compressive stress. Here will be maximum compressive stress. So sigma in point A will be that QYL squared over 2. Now distance here from here to there is 3. Then bending moment of inertia, 2, 6 cubed over 12. Plus, okay, that is this plus. So that is this plus. This plus comes from here. This plus comes from there. PZL times 1, because the distance, this whole thing is 2, so it's 1. 6 times 2 cubed over 12. Okay, one can do the calculations. You can do calculations if you want. Length equals 3 meters, QY equals 100 kilonewtons, PZ equals 1,000 kilonewtons. You will get the stress. Any questions? Yes, that is correct that you are not here. Not only you are not here, but you even do not know where I am. And I will tell you where I am. That is interesting. That is a professor's migration. We started in General Classroom South 101. Then I was moved Fleming Hall 401. Now I'm moved to CM building, computer building 128. So, as a result, I'm in 3 different places during this semester. We started together. Then we became together alone. We are together in this problem, but we will overcome because we are together. Any questions? Okay, I would like to address, since I said that we are together, I was asked by a student if she can submit homework a bit late. My answer is yes. Another question, I was asked I will put my answers today on Canvas, but I would like to say it immediately because maybe you are waiting and you may think, oh, he did not put this information, did not answer me. I just saw before I arrived to this class about this. I was asked by a student if we can postpone submission deadline. And deadline of project 2. Deadline, of course, is deadline April 9. So I'm moving it. So he said that he is struggling. He is struggling with project. So I'm moving the submission date April 13, 2020, not later than 5 p.m. Okay? I did not have a chance to start to check the test. I will start today checking the test and project 1. Please pay attention that I devised a system in which every student can succeed. Past semester in vibrations, no student failed. Semester before in statics, no student failed. Means, what does it mean, no student failed? Some people left in the beginning, 2 or 3 students left in the beginning. I did not even converse with me, did not have even one test. They are leaving because their schedule maybe is different or something like that. Anyways, no one left because of academic performance. However, this is because somehow I was able to motivate them to work hard. Hard work will take us very far to the success. Okay, yes, we can combat not only coronavirus, but naturally and successfully intermediate strengths of materials. Yes, we can do it. Okay, any questions? That is from actually today's newspaper. Okay, we are coming back to skew bending. Skew bending can be considered as a superposition of 2 direct bendings due to mz and my. So then stress equals normal stress equals normal stress due to mz plus normal stress caused by my. So I'm bringing you an example. Look, that is this cantilever beam. So here is P1, 100 kilonewtons. Then there is a moment, bending moment, M that is in Z with respect to Z axis, equals 200 kilonewton over meters. Then this is distributed load 20 kilonewton over meter. Here there is a load in other directions than we had before. And then another load here. So I'm depicting MZ diagram, approximately. So that is, this load causes this load. Straight line. Then because there is a moment, we have the jump. Okay. Then from here, we have this distributed load, gives me this value. Okay. Now here, that is my. My, this load gives, now we are depicting it in ZOX plane. So this gives me 200 times distance. Okay? That is a straight line. Then there is, okay, this is. Then there is another slope, change in slope. Okay, and then we have to find where is the maximum stress is occurring. So that was just an example. But now I will consider another example, one more example. Any questions? So that is why, if you remember, we needed bending moment diagrams, shear force diagrams, etc. Why? Because we need to calculate beams for various stresses. What happens when we have a circular cross-section? Now, circular cross-section is an important consideration. So imagine we have this, so I am again considering cantilever because it's easier. So load F and 2F in Y direction. This F in Z direction. So that is A, that is 2A, and this is 2A. So what will be the diagram? That is MZ. F times, so here 2A, that is 2AF, this one. Then here will be this F times distance is 4A, 4AF, plus this 2F times 2A is 4AF, so it's 8AF. So this equals 8AF. Here, that is MY. So that is this force times, so that is A from here, that means that from here to here is A, and plus 2A is 3A, so 3AF. So then pay attention here then, that is the maximum moments will appear in the clamping. Maximum values in clamped end. Okay? So then there is this moment with respect to y-axis, and there is a moment with respect to z-axis, that is z. Moment. And that is this one. So then, according to the Pythagoras, I'm not calling him great Pythagoras because do you remember what he did to Hippasus? Was very clever, but not a nice guy, not at all. So then we can actually imagine that this, instead of these two moments, we have just one moment. That is a resultant moment. That is equivalent moment. It is equivalent to both of them. That means that we can replace these two by one. That it means that they're equivalent. So then it is mz squared plus my squared. That is geometric summation of two perpendicular vectors. Any questions? If you have no questions, then if I have a circular cross-section, then Iz equals Iy equals pi c in force power over 4. That is a radius. Yeah, radius. That is C. So we want to check strength. How much is strength? Sigma. So instead of M, we write M equivalent over M equivalent divided by I times C. So I is this, pi c in force power over 4, so that is C. So then we get mz squared plus my squared, pi c cubed, because c in force power divided, so c cubed. Now, this is now the main thing. This should be compared with sigma y divided by safety factor. Oh, factor of safety. So usually, that is usual name. And that is Hibbeler's name. Any questions? Now you see that prerequisites are prerequisites. Are super important. Please review chapter on bending in your book, which is electronically available. Freely. That is what I like about freely. That is why I adopted 9th edition. Publisher phoned me several times and asked me to adopt 10th edition. And they sent me a 10th edition, free of charge. However, I said that this using 10th edition would contribute to further inequality and inequity between my students. And I do not want students to spend money on this and therefore work more hours and have less time to do homework. Again, I'm repeating the best thing student can do in April is, if it is possible, not to work until the examination period ends. After examination period ends, if there is a work, then please work many more hours. Now it's time to devote to succeed in all courses, not only this course. Any questions? Okay, I'm continuing further. I will consider some example. See, today I'm doing lots of examples. Example, find existing or actual, that is the same. Existing or actual. Factor of safety in a dangerous. I was looking at this word and I did not recognize it. Dangerous. Probably I am writing and thinking ahead and I left out the letter. Dangerous point of a beam shown in the figure. That is this figure. Look, what is this? It's a very innocent problem, as it were. There is this 2F here, vertical force, and there is horizontal force, but it is acting not centrally. Okay, 8F. Yield stress of material equals sigma y equals 2,240 megapascals. Demanded factor of safety equals 1.7. Okay, C equals 0.3. F's are given. So this is F3 equals F equals 2.5 kilonewtons. That is this one. Here that is 2F. Here is 8F. This is 3 meters and that is 3 meters. Okay, I will depict free body diagram. Free body diagram means we are getting rid of constraints. You cannot make this picture on here because then it is not free. So therefore, if you make these numbers here, that means that you don't understand what strength of materials or statics is, and therefore it will not lead to success at your work. So free body diagram is a beam separately. So there is this load 2F, which equals 5 kilonewtons. Now, this, with respect to z-axis, this load yields to the moment. That is, okay, so there is also an axial force, 8F, which is 15 kilonewton. And this is this 8F, which is 15 times 3, because radius equals 0.3, sorry. 0.3 times 15 equals 4.5. That is kilonewton meter. Okay, now that is this load 2.5. Now here, there is this my. There is my. So that is, this load is 2.5. Therefore, bending moment reaction is 2.5 times 3. So that is 7.5. There is also, of course, force here in the direction. That is this one, reactive force. That is 2.5 kilonewtons. That is this, opposite this force. Then there is a force here up, that is 2 point, so there is this reaction, which is 5 kilonewtons. And then, of course, there is a bending moment, mz. Where is here mz? Okay, we will get this mz. So I'm depicting diagrams. That is nz, n sub x. That is axial force. Because there is this force in axis direction, then there is this axial diagram of axial forces, which is extension. So that is plus. And that is 15. 8F equals 15 kilonewtons. Then there is this MZ diagram. MZ diagram equals, look please, we start here, I cut here, I get this 4.5. Then this force leads to reduction, so we get here, will be, look please, let us look here, 0.45 minus 2F, which is 5, times 6. So it will be yes, 0.45. Then yes. So will be 0.45 minus 30. Why did I write 0.45? This equals 4.5. Sorry, 4.5. 4.5 minus 30. That equals 25.5. So that is the straight direction. Now my starts here 0, and that is times 3, 7.5. So that is my. You see, to design system is not so trivial. Any questions? So I just did this calculation. Oh, here should be minus. mz equals 4.5 minus 5x. Because it's 2f equals 5. So these are the diagrams. Now we will calculate the stresses. Now, by the way, yeah. Okay. So what we have here is skew bending plus extension or tension. So sigma x equals nx over a, that is due to axial stress, plus m maximum I c. So nx equals 6f. So 6 times 2.5 equals 15 kilonewtons. How much is m maximum? Equals mz square root. Mz squared plus my squared equals 25.5 minus 25.5 squared plus 7.5 squared. This equals 650.25 plus 56.25. That equals square root of 706.5, which is approximately 2658. As you pay attention, I'm giving in this course a lot of examples. Why? Because examples are, because at the end, in your practice, you will have to deal with numbers, with calculations. Yes, theory is super important, otherwise you cannot write any numbers. But numbers themselves are also very important. So then sigma maximum equals 15 divided pi r squared, that is area, pi times 0.3 squared, plus 26, that is a bending moment, 58, then pi 0.3 in forced power over 4 times 0.3. So that is 53.0.5, this one, plus 1,253.47. So equals 1,306.58. How much is an actual safety factor? Actual safety factor is defined as sigma maximum, sigma y divided by sigma maximum. So that equals sigma yield divided by sigma maximum. 2,240 divided by 1,306.52 equals 171. So now, if you remember, I said that required, demanded safety factor of safety equals 1.7. So actual safety factor is bigger than required safety factor. Strength requirement is satisfied. Any questions? Now I will get to safety factor issue. Three basic problems of strength of materials. I will describe now, there are three types of problems at all that you are encountering. Now it makes sense to look back, so to say. Like people in more mature age write memoirs. Bill Clinton in his book, My Life, said that everyone should write a book about his life. Some person's book will be short, he wrote, maybe 12 pages. Other people's books will be heavy. But we can look back and make some conclusions about two courses that we studied. Strengths of materials and advanced strength, and intermediate strengths of materials. And that is, there are three types of problems in strengths of materials. And they stem from this one innocent inequality. Sigma should be not greater than sigma allowable, smaller or equal. And that equals sigma y divided by k, required safety factor. I took it in square parentheses. Why? In order to underline that that is required. Before, we said just actual safety factor, what you have in actuality. So problem type 1 is checking strengths. So previous problems that we solved, it was this type of problem. Loadings are given, material properties are given, geometry of the problem is given. What should I find then? Come on, everything is given. So what should I do? Okay, find if strength requirement is satisfied. So that is checking. Or maybe I should say, I should write instead of find, check. Check if strength requirement is satisfied. Now, actual factor of safety, FOS, also denoted FS, K, that equals sigma y divided by sigma maximum. So that is like this. That is sigma y. So that is sigma maximum. How many times sigma y is bigger than sigma maximum? So that is actual safety factor. That is a definition of the safety factor. Interestingly, surprisingly, Professor Hibbler and many authors do not distinguish you remember, I like to use word distinguish rather than discriminate, because the word discrimination is always understood by us in very negative context. So, does not distinguish between actual safety factor, actual factor of safety, and required factor of safety. Interestingly, I wrote him already in 1995, which is 25 years ago. Many of you were not born at that time even. He agreed with me and did not change exposition in his books, further editions. He did make other changes. And thanked me in next edition. Not the latest one, next edition of the book. I don't recall which edition is that, but I can find, I think that I have these letters. I have this correspondence. I will bring that. I have this correspondence. And we'll show you in coming lectures. Okay, but that is a very important topic because it is used in design very, very much. By the way, I will tell you also that committees, that is industrial committees, industrial advisory boards, advised us for years to introduce intermediate strengths of materials. And finally, it was introduced starting this semester. So I am the first lecturer to teach it. So, because this material, they were saying, is desperately needed at work. Okay, anyways, there is a book that I wrote, but it's more advanced. These topics, what we consider, these are elementary topics that we are considering here. But I wrote a book that is the first and only book in the Western literature on safety factors. So that is safety factors and reliability, friends or foes. So this considers safety factors on one hand and probabilistic design of various structures in aerospace engineering, civil engineering, ocean engineering, civil engineering, and automotive engineering by Dutch publisher, Kluwer Academic Publishers. Okay, we continue. If actual safety factor is greater than required safety factor by codes, then we conclude that strength requirement is satisfied. So that was problem 1. Problem 2. Everything is given except some parameter or actual value of the load. So that is called, problem 2 is called finding maximum allowable load. What kind of load this system can undertake? So it's a very important question. I will have this system. This system will be operating in various circumstances, including hurricanes, winds, ocean power, and whatnot, turbulent excitations. What kind of load this can take? Okay, find maximum value of that parameter, P max, so that strength requirement is satisfied. So, pay attention, there is one more. Third problem is design. Everything is given except some geometric parameter of the cross-section or cross-section itself from a given list of profiles. Okay, for example, it says only that it is I-beam, but does not say which I-beam. So we have or checking stress, or checking strengths, or finding maximum allowable load, or design the beam. Everything is given except some geometric parameter of the cross-section or cross-section itself from a given list of profiles. Find minimum acceptable value of the geometric parameter so that strength requirement is satisfied. Minimum, because if you are increasing cross-sectional area infinitely, naturally the strength criterion will be satisfied. We do not want to overspend. I want to find what is the minimum value. So at least I know how much I should spend without any hesitance. Any questions? There are 3 types of problems. Every problem falls in one of these categories. So that is like looking back. At life in strengths of materials context. Any questions? Now we come to strength criteria, and one criterion we already discussed. That was maximum stress criteria. So, stress criteria. We should know the stress criteria really like very good friends of ours. Pay attention. Stress criteria or strength criteria are our real friends. Why? Because we will design correctly by certain criterion, and we know that system will stand, system will hold, system will perform its mission. There are also some imaginary friends, of course. Okay? Let me show you. Turning imaginary, because that is from FAU, I cut, I don't know where from. It says turning imaginary friends into best friends. So imaginary friends, of course, these are number I, do you remember? So this I now, you know how to, so we need both. We need both mathematics and we need also the design. Okay, we need both. We need both mathematics and we need also the design of the system. (2113A). 2113B. Okay, strength. First is naturally theory of maximal stresses. So pay attention. We have a stress state. What is a stress state? Is we have an element. An element is under various stresses. How do we calculate stresses? From forces and moments. So stresses come forces and moments. So when we talk about these imaginary friends, forces, moments, are also imaginary friends because no one ever saw a force or a moment, as well as I. So pay attention. Now, this is an element. Then, pay attention, this is sigma x. So that is x-axis. Now, there are also shear stresses. Now, I will tell you how do we denote shear stresses in z direction and y direction. Okay, this is y, so that is y direction. So pay attention, we give index. First index is x, that is a, pay attention, these are in the face, which is perpendicular to x-axis. So that is the first address, perpendicular to x-axis. This is in z direction. This is in y direction. So tau xy, tau xz. Again, it acts in the face, which is perpendicular to x-axis. Now here, they are acting in the face, which is perpendicular to z-axis. That is x-axis. So therefore, there is x. Here is, so first there is z. Then this one is zy, because in y direction, that is a direction. That is x, etc. Then there are forces here like this and like this, shear forces. So in total, pay attention, in total, in every point, there are 9 different stresses acting. Sigma x look please here, sigma x, then tau xy, and tau xz. So I put everything in one line, what acts on this face. Then we have sigma y. So this is, look please, let us make notations. That is tau. Perpendicular to this face is y. So this is also tau y. Now this acts in x direction. This acts in z direction. So here I will put what is there. Tau yx, sigma y, tau yz. I wrote what is written in this face. So I will write what is on this face. Tau zx, tau zy, and sigma z. What is this? Okay, so that is a stress state. Now, in strength of materials we learned, but now I'm considering even more general case, that this condition can be transformed to a condition which is easier for us. Why? Because we are lazy. I don't want to deal with 9 quantities. If I negotiate some treaty, I don't want to deal with 9 people. I prefer to deal maybe with 3 people. It's easier to get to an agreement. So greatest, so that is so we can transform this condition, so we can rotate system in such a manner that we will get sigma 1, sigma 2, sigma 3 here. Only normal stresses. And shear stresses are 0. So principal stress and sigma 1, sigma 2, sigma 3. Rankine, famous English engineer Rankine, said, that is end of 18th century, I think 1887, something like that. No, 1865 to 1887. First time his book appeared, I think, in 1865, and second edition, 1887. Rankine. Okay. Greatest principal stress, that is, greatest principal stress theory, or maximum normal stress theory. Theory of maximum normal stress. Okay. So you see nearly whole page. Any questions? So that is the first theory of strengths. So there is sigma y, sigma 2, sigma 3. This is equivalent to this condition. Do you remember we have experiments for this one? We have experiments available for this one. For uniaxial tension. Okay, then sigma here, maximum, is equivalent to sigma equivalent. So that is what Rankine says. So sigma maximum equals sigma 1. So sigma 1 is actually connected with equals to sigma equivalent. And then equals sigma y divided by k required. K required, that is a required safety factor. It is called maximum normal stress theory, or maximum normal stress strength criteria. Theory is let us say, unsuccessful term. Because that is not a theory. We did not have any theoretical considerations. Rankin just said, what is important is maximum. The rest is not important. Interestingly, analogous, so to say, theory was considered by, as it were, some analogy. Some analogy. After French Revolution, at French universities, they adopted the following system. The grade of the entire class was equated to the grade of the best performing student. So they were interested with maximum. That is, of course, very weird approach. Okay? That is very weird approach. But anyways, that is what they did after French Revolution, because they had no time to study. They were making revolutions, etc. So they said that students' grades should be like this. No country has adopted, I think, since then. Now, pros. What are the pros? It takes into account maximum stress. So that is a pro. Maximum stress is not overlooked. Maximum stress is not overlooked. Okay, it does not take into account any other stresses, other two stresses. Like there, they were interested in the best performing student. I did not say best student, because best performing student is not always a best student. Because there are some students who can be the best, but they do not know how to take the test, get anxious, or they don't like to perform in very pressed condition of 1 hour or 1 hour or 20 minutes or 50 minutes. So according to this criterion, these two states, say, imagine there is an element that has only one uniaxial stress, 1,000. And here is 1,000, here is 999, sigma 2, and sigma 3 equals 998. So Rankin does not care about this 999, 998. He cares only that there is 1,000 here, and here is 1,000 is maximum. So from his point of view, this condition and this condition are equivalent to each other. Because sigma 1 here is 1,000, and sigma 1 here is also 1,000. So this theory is insensitive, as it were, to weaker stresses. Any questions? Okay, we continue. Then, second one is maximum linear deformation criterion. So I have this stress and this. So here is sigma 1, sigma 2, and sigma 3. So here is sigma equivalent. So then deformations look, please, in one direction. Epsilon 1, according to Hooke's law, there is sigma 1 over E. But when I'm extending, when I'm applying sigma 2 in this direction, in y direction, then element shrinks in x direction. So this shrinkage is identified as minus nu sigma 2 over E. This is Poisson's ratio. Okay, Poisson was a French engineer. Analogously, when sigma 3 is extending, then here in x direction there is a shrinkage. There, and it's analogously minus nu sigma 3 over E. So there is epsilon 1, then there is epsilon 2, which equals 1 over E, sigma 2 minus nu sigma 1 plus sigma 3, and epsilon 3, 1 over E, sigma 3 minus nu sigma 2 plus sigma 1. Here there is only linear deformation. Sigma x equals sigma equivalent over E. So that is maximum or greatest principal strain theory. So this value equals to maximum. This is maximum. Why? Because sigma 1 is the biggest. So maximum equals epsilon 1. So epsilon 1 here equals epsilon 1 here, maximum here. So here 1 over E sigma 1 minus nu sigma 2 plus sigma 3 equals sigma equivalent over E. So sigma equivalent equals sigma 1 minus nu sigma 2 plus sigma 3.